Linear equations and functions. Section 1, relations and functions. So a relation is a pairing of input values with output values. The majority of the time we will represent these and have represented these in the past as a set of ordered pairs or points that you could put on a graph. Along with points that you've put on a graph in the past, we've talked about domain, which, as a reminder, is the set of all the input values, or those x variables, the x coordinates from the ordered pairs. These are also referred to as the independent variable. And the range is the set of the output values, or the y coordinates from the ordered pairs. And this is the dependent variable. So in the next example, we're given a relation as a list of ordered pairs. And our first task is to identify the domain and range. So before we actually go into identifying the domain and range, first thing we have to realize and understand is that when we write these lists, we're going to list these values from least to greatest, and we are going to not repeat any values. So if a number shows up more than once, we're just going to list it one time. So for the domain, we have to remember again, the domain is the set of the input values, or the x coordinates, and listing them from least to greatest, we would write this list. We would have -2, -1, 1, 2, and 3. Then listing the range, again, we would list from least to greatest, but now we are looking at the y coordinates of the ordered pairs given to us in that relation. And that list would be -3, -2, 1, and 3. And again, hopefully you realize the 1 was a repeat in the range, and we only listed it one time in our list for the range. Another thing we can do with a relation is represent it using a graph, and this is actually something you've done plenty of times before. All you have to do is graph each point of that relation individually, and then the graph as a whole represents the entire relation. So if we were to graph the point -2, -3, and then we can graph the point -1, +1, and so on until we have all 5 points on the graph like you now see. This is just a visual representation of what that relation would look like. Another representation we have for relations is called a mapping diagram. A mapping diagram works along with the ideas of domain and range, but shows them, kind of organizes them slightly differently, and then there's an extra piece to it as well. So the majority of the time, when you're given a mapping diagram, you'll kind of see these, I don't know, oblong shapes, kind of almost rounded rectangles, whatever you want to use to describe them. In my opinion, you wouldn't even have to draw those if you just want to make basically vertical lists of your input and your output. That goes along with a mapping diagram just fine. So you're going to have 2 columns, 2 lists, one of them labeled input on the left, output labeled on the right. Then within the input and the output, you're going to list your domain under the input and your range under the output. And when you make this list, it's kind of the same idea as what we wrote earlier. You want to use all those values without any repeats, and generally it helps people stay more organized when you list them from least to greatest. So here's what the list of the input values would be, or the domain values from the relation that we were given. And then again, in the other column on the right, we'll list the output values as well. Again, least to greatest, staying nice and organized, not showing any repeats. From here, the extra piece of a mapping diagram is it actually shows you with a line or an arrow connecting an input value to its output value, which pieces are actually related. So for example, if we look at the first point in the relation, -2, -3, in our mapping diagram, to show that those are the input and the output values that are paired, we would connect them from the input value to the output value by drawing an arrow. And then we would repeat that for every input value from every ordered pair that we have in the relation. So if I were to complete that for all the rest of my values, we would have this mapping diagram. And again, each of those arrows would just be drawn individually based on each individual ordered pair in the original relation. Now, a function is a type of relation, but it's a specific type of relation. In a function, each input has exactly one output, or another way of saying it, each x coordinate has exactly one y coordinate. You cannot have the same input value or x coordinate connected or related to multiple different output values or y coordinates. So now looking at the previous example, number 4, can we say that that relation that we were given is a function? One of the easiest ways of doing this is with that mapping diagram. So you're looking at that mapping diagram and you're asking yourself the question, is there any input value that has multiple arrows that point to different output values? And this one does not. So this one is a function. So we can write, yes, it is a function. Then the explanation can be simply each input or x value has only one output or y value. So now continuing our work with determining whether a relation is a function, using this mapping diagram in 6a, is that relation a function? This relation, is a function because each input has exactly one output. It does not matter that we have two different inputs pointing to the same output. That's fine. Each individual input has to have only one output value. That's what we're looking for. So now in part B, does this mapping diagram of this relation show a function? This one is not a function. The reason it is not a function, our explanation, is that 1, which is one of the input values in the left column, has two different output values. It has two different arrows from 1 pointing to -1 and then 2 in the output column. Another way of determining whether or not we have a function is using what's called the vertical line test. Right? So a relation is a function if there is no vertical line that intersects the graph at more than one point. So this is more of a visual one. When you have a graph, this is the method of kind of a test that you would want to use. So what you can do, whether it's physically putting something on the paper and having it vertically on your graph and moving it left to right, or just kind of mentally doing it, you want to take a vertical line and pass it from left to right over the entire graph and check to see if at any individual or any specific time, and all it takes is 1, does that vertical line hit the graph at more than one point. In this particular graph, this vertical line does not hit the graph at more than one point at any time. So this graph is a function. It passes the vertical line test. The function in the middle, if I were to move this vertical line across, it only has to happen one time. Here you can see it happens multiple times, actually an infinite number of times. This vertical line is intersecting that graph at more than one point at a time. So this one fails the vertical line test, so is therefore not a function. How about our third example? Would that represent a function? If I take this vertical line and I pass it across the graph, remember all it takes is one instance of that vertical line hitting more than one point at a time. So here it hits 2 points at a time, and over here at -4 it hits 2 points at a time. This fails the vertical line test and is therefore not a function. Next, within equations, linear equations and functions, we deal with the linear equation, excuse me. These are equations where the x variable has an exponent of 1. These are, because of the name linear, these are the equations that when you were to graph them, which we will do shortly, you are graphing a line. A nonlinear equation are equations where the x variable has exponents other than 1. So if you have an exponent of 2, you have x squared, for example, that would be a nonlinear equation. Maybe if you think back to algebra, you did some work with graphing. They're called quadratic equations, the x squared equations. Those graphs were parabolas, the U-shaped graphs, not linear because they are not straight lines. Along with these functions and different types of equations, we can use what's called function notation. This is where we use something like f of x instead of y. The reason being is because this tells you exactly what you are plugging in for, in this case, your x variable. So that's what the notation is actually used for, why it's a little bit more useful. It actually gives you a little bit more information at times. So below here you can see slope-intercept form. Hopefully you're familiar with this, or at least kind of recognize it now that we're reviewing it. Slope-intercept form, just using our regular notation, is y equals mx plus b. But now if we use function notation for it, you can see it's f of x equals mx plus b. The actual form of the equation did not change at all, other than replacing the y with the f of x. So what you are going to be asked to be able to do at some point is to be able to evaluate an equation or a function given a value for a variable. And what this simply means for you to do is to take that value of that variable and plug it into your equation. So if we have the equation y equals 6x plus 2, and we're told to evaluate that when x equals 2, it's very directly telling us what to plug in for the x variable. So what we would need to do is show that we are substituting that value into our equation where we see that x variable, and now we use order of operations to evaluate that, simplify it. So the first thing we'd have to do here is take the 6 times the 2 and get 12. Then we would add 2, and we would have y equals 14 as our evaluated answer. Now, if we look to the right, this is asking us to do the exact same thing. It just looks different. It's worded differently because it doesn't have to tell us the value of the variable separately like it did before, because with function notation, we can see right here inside the parentheses which value it is we are supposed to be plugging in for the x variable. Again, this is the whole purpose of using function notation. So when we evaluate this, once again, this is the exact same problem using different notation. So we're told to plug in 2 for x, then we have to follow order of operations and simplify this to get 14 once again. But now notice, when I write my final answer, if the original function was in function notation, really your final answer should be in function notation. And this is actually more useful than looking over here to the left, because we are told both our input, which is 2, and its associated or paired output of 14 all at once, instead of having to possibly look back and be able to identify it from doing a little bit extra reading again. So now I'd like you to try this. Tell if this function f of x equals x minus 1 minus x cubed is linear. So now this one is not linear because of the exponent of 3. So this one we'd have to say is not linear if we're ever asked to give an explanation. We would have to say x has an exponent other than 1, or you could specifically say that it is an exponent of 3. Now, our job is to use that function and evaluate f of 2. So please do that. So the work that you would need to show for evaluating f of 2 in this case would be showing that you are first of all plugging 2 in for each of the x variables in that original function. Now we follow order of operations to evaluate or simplify this. So the first thing we'd have to do is the exponent. 2 cubed is 8. So 2 minus 1 minus 8. Now we are just subtracting left to right. This would result in a final value of -7. So really, again, we were given function notation. So ideally, our answers would be in function notation. So f of 2 equals -7. The next piece that we're going to review is the idea of the x and y intercept idea, and then how to use those to graph a linear equation. So hopefully you recall that an x-intercept is the point where a graph intersects or crosses the x-axis, kind of hence the name. And then also, hopefully you recognize or remember that any x-intercept point has a y value, a y coordinate of 0. A y-intercept, very similar to an x-intercept, except now these are where your graph would intersect or cross the y-axis. And in any y-intercept, the x-coordinate is always 0. So if we're to graph equations using x and y intercepts, one of the ways that you can do this is using what we call an intercept chart or a t-chart. And in this t-chart, because we're going to use intercepts, there are very specific values that we have to plug in for our x and y variables. So first off, if we were to do the y-intercept, we would have to plug in a 0 for the x coordinate. So we would be thinking that we would have in our equation, which is given to us, plugging in 0 for the x coordinate, then evaluating that, 5 times 0 is 0, minus 3 is -3. We would have the y-intercept on our graph at the point 0, -3. So 0, -3, we would have our point right there. Next, we could do the x-intercept. And the order of these really doesn't make any difference. But if we're using or finding the x-intercept, we now have to replace the y variable with the 0, because any point along that x-axis has a y coordinate or a y value of 0. Now we actually have a little bit of work to do to solve this, and this could be mental math. I fully understand that. But we have this value of 3/5 for our x-coordinate of our x-intercept. Now the issue with 3/5 is that it's not a real easy value to graph. You kind of would be estimating. So in a case like this, you may want to find a third point. You can find this third point by plugging in any x value that you'd like other than either x value from the intercept. So I can't use 0 and I can't use 3/5. So one of the easier values to use would be number 1. So if I want to plug in 1 for x, I would just again have to use order of operations to simplify that. 5 minus 3 would give me 2. So I could use this third point to help me be a little bit more accurate with my graph, and actually have the ability to show really closely where that x-intercept would be. So I know 3/5 is a little bit more than a half, so I could kind of estimate that the point would be about there. But again, using a third point in this case will help you be a little bit more accurate. So now, again, realistically, that third point is optional, really is most useful when you have an intercept that's not a whole number or an integer that's nice and easy to graph accurately. But hopefully you recall that you really only need two points in order to graph a line. So we're going to graph the line here for the equation that we were given. And I would like you to be sure that you are using a straight edge to draw the line, because we do have to have accurate graphs. So using a straight edge will help you be more accurate. It'll ensure that your line is straight. So that is going to be an expectation. So again, 2 points is all you really need. I did a decent job here of estimating where that x-intercept would really be, even though it was a fractional value. Moving over to part B, we're asked to do the same thing. So again, we can set this all up. You don't have to label all of this when you do your own. This is, again, just for note purposes. So if we wanted to find here our y-intercept, we're plugging in 0 for the x value, or again, if this is in slope-intercept form and you recognize that, you probably can pull that b value, y equals mx plus b, out right away. And if I graph that, 0, positive 2, there's my y-intercept. If I go to the x-intercept and plug 0 in for the y, and then work through and solve this, I'd be subtracting the 2 and then multiplying by the reciprocal, which would be multiplying by 2. So negative 2 times 2, I would get a value here of negative 4 for the x-coordinate. So negative 4, 0 would be the point here on the x-axis for my x-intercept. Now, both of those points were pretty straightforward and very easy to graph accurately, so there wouldn't be a real reason for the third point in this case. However, if you were to want a third point, there's nothing wrong with that, but I would really encourage you to, before you just pick a random x value, think about what you're doing for a second. Look at the equation. The first thing that would have to happen with your x value that you select is you'll have to multiply it by a half. So to, again, make this easier on yourself, pick something that would actually multiply it by a half or divide by 2 nicely. Pick something like 2 or 4 or some even number, positive or negative, that you won't have to be dealing with fractions when you go back and actually plug it in and evaluate. But again, that's not totally necessary this time because we have 2 nice points here for us to graph. So then we would just, again, take our straight edge, connect our 2 points, and show that this would be the line from graphing that equation. The last thing we are going to do for this lesson is go back to the idea of domain and range initially and use a table that's given to us here, another way of showing a relation instead of ordered pairs or a graph or a mapping diagram. Tables are often used. And now we're going to identify our domain and range. So here, if we are using the year that a bridge is completed as our x-coordinate, our input value, and the length of the bridge is the y-coordinate or the output, what are the domain and range? Again, remember what we talked about previously. When you list the domain and range, you always want to go from the least to the greatest value without repeating any value. So again, if a number shows up more than once, you only write it down one time. So here the domain would be 1931, 1937, 1939, 1957, 1960, and 1968. The range, the length values, would be 2150, 2300, 3500, 3800, and 4200. Again, notice the value of 2150 showed up multiple times. That's the length of both the Delaware Memorial Bridge and the Seaway Bridge, but we only list it one time in the range. Now, from this relation, now that we are kind of investigating it a little bit, is this a relation that is also a function? This relation would be a function because each input is mapped to exactly one output, or each x value has exactly one y value. There is no bridge built or in bridges built in the same year that have different lengths. But now, I ask you to think about it a little bit differently. If we flip-flop these and we make the length of the bridge the input, notice here in the ordered pair we have the y first. If the length of the bridge is the input and the year the bridge was completed is the output, is that relation a function? In this case, this would not represent a function because the length 2,150 feet would be mapped to both 1960 and 1968. Therefore, not making it a function, it has two output values.